Thanks for coming to the talk. We're going to talk about Art, L's runtime, replacing Dalvik. Hopefully you'll leave with a better understanding of what Art is and what improvements you can expect. We'll also talk a bit about 64-bit support in Art and in the platform at the end. So I'll be presenting today along with my colleagues, Brian Carlstrom and Ian Rogers from the Android Runtime and Tools team. I'm Anwar Ghuloum. They'll talk about different aspects of the runtime. They'll be coming up pretty shortly. Thanks, guys. First, why Art? So when Dalvik was originally designed, the processors we were targeting were single-core, relatively poor performance, relatively little flash, and RAM available. But things have changed, right? We had a compact bytecode that was designed for fast interpretation, relatively unsophisticated GC, and it wasn't designed for multiprocessing. But since then, what we've seen is we've got phones shipping with 8 cores. We've got devices that have improved in performance over the G1 by 50x or more in terms of raw CPU performance. We've got 4x more RAM, sometimes more, 64x more flash, higher resolution screens, extremely powerful GPUs. We made a lot of changes in Dalvik to improve things, right? We added a JIT, we added a concurrent collection, garbage collector, and we added support for multiprocessing. But we felt, frankly, that the ecosystem was outpacing us, that we had to do more. So Art was born. So our motivation for Art is that you shouldn't notice the runtime at all, right? Your app should be buttery and smooth, even though you're using GC. Code should be fast without having to resort to JNI or native code. Startup time should be fast without having to warm up a JIT, and so on. The runtime in general should scale to the parallelism of modern processors, as well as the complexity of modern mobile applications. In other words, it should be a really solid foundation for the future. So in this talk, we're going to start with telling you about performance and compiling in Art, how Art compiles ahead of time, and what kind of performance improvements that brings you. We'll then talk about the garbage collector and how GC'd apps can be buttery and smooth. And then we'll talk a bit about 64-bit. So with that, I'll hand it over to Brian.
Thanks, Anwar. So I'm going to start by talking about a user. We have this public bug that's one of our favorites on the Art team. It's a user wanting a performance-boosting thing. And if you read the details in the bug, they want to take their existing phone and their existing apps, and they just want to get a system software update, and they want faster performance for their apps, they want better battery life, they want to use less memory so they can multitask more. And we really like this bug because it really matches well with what Anwar said about the Art manifesto about trying to transparently improve performance for apps without people having to do anything. So, what can we do about that? So as we've already said, we started with Dalvik, and it had some performance boosting things. It had a fast interpreter. JIT was added, another performance boosting thing. And what can we do for Art? Like, what can we do going forward? And we said, well, Dalvik was built for really targeting ARM. Now in more modern devices, we have a lot more APIs we have to support. We want to do potentially different optimization levels for different use cases. So rather than just trying to build one performance boosting thing, we want to build a framework of performance boosting things. And so we're going to build a kind of flexible compiler infrastructure that can allow us to do that. So this is just a little box diagram of what we're doing with the Art compilers. As you'd expect, we have a front end that can read our DEX bytecode for compilation. We have a compiler driver, and that's what's interesting, that it directs to various different compilers that are available in L. And we have 3 main compilers that we're using in L, but there's already seeds in the AOSP code for other compilers that we're working on for the future, seeds of future performance boosting things. What we have for L is a compiler we call the Quick compiler, which is based on the old Dalvik JIT, so it does many of the same things, but it does more than that, and we'll talk about that in the next slide. It focuses on compiling your DEX code to native ARM code, x86 code, MIPS code, et cetera. We also have a JNI compiler that helps build bridges from your DEX code to any native code you've done with the NDK. And finally, we have a DEX-to-DEX optimizer, which just quickens code we decide not to compile that we just want to do fast interpretation on. In addition, we have to have, like I said, numerous backends, and so we're supporting the 32-bit ABIs that Android currently supports, as well as the new 64-bit ABIs that are coming in L. So what are the benefits of some of the other benefits of doing ahead-of-time compilation? One big difference between ahead-of-time compilation and the JIT we had in Dalvik is that we optimized the whole program potentially. and that instead of just focusing on small traces of the program, loops or things like that. So the kind of optimizations you do when you're targeting like small parts of the program or loops are very different than when you're trying to do the whole program. And we try to do optimizations that can generally apply to all kind of object-oriented programming that you might be doing in Android. And so some examples are we try to make virtual method calls faster when possible. We try to lower the overhead for interface invocations. We try to avoid some implicit checks that need to be done when you're calling from one class to another to make sure it's initialized, when you're calling constructors or static fields, accessing static fields or calling static methods. And finally, there's a lot of things that are sort of implicit checks that are done in object-oriented languages to throw null pointers and uncommon cases and stack overflows and things like that. So we try to make all those kind of common case things faster so it can improve the general performance of your program. But we've also seen some other benefits from ahead-of-time compilation, those things that the user wanted. We do see better battery life, and there's two reasons for that. One is because we're compiling, and only at installation time we compile once, as opposed to a JIT-based environment where every time you run the program, it typically re-JITs, rediscovers things, redoes work. It's kind of wasteful every time you run your program to redo the same compilations. Second thing we see is that generally faster performing code saves battery because you can more efficiently run and get back to a lower state on the processor quicker. We also see a better Svelte memory footprint. If you remember Project Svelte from last year, trying to run better on lower memory devices. The reason we see better Svelte numbers are because the code is written out to disk and can be paged in and out by the kernel on demand. If there's a lot of applications running multitasking, the kernel can kind of manage paging things in and out, as opposed to the JIT where there would be a kind of set of private pages per application, which couldn't be paged out, so that meant that if the kernel needed to free up more memory, basically has to kill a process and you lose one of your processes you may have trying to multitask between. So how do we do that? This shows the life cycle of an APK, the Android package that comes from developers to the users. And so the typical steps in the APK in the life cycle are you take your source code, you compile it, you make a DEX file, you can combine it with native code from the NDK and resources, and you basically put in a zip file we call the APK, and that gets distributed through Google Play to the user. So on the user side, they take it and they install the application. And the native code and the resources generally get unpacked into the application directory, but the DEX code requires further processing. And this is true both for Dalvik and for Art, as you see here. In Dalvik, they ran through a tool called DEXOP during installation, which already did some ahead-of-time things. It did ahead-of-time class verification. Again, it tried to quicken things up to improve performance for the interpreter. Dex2Ode is the tool that Art uses, and again, this is sort of transparent behind the scenes, but it compiles the application. It does, in addition to doing some of the things that Dalvik did in terms of verifying things ahead of time and quickening things, it also does that compilation to native code for the target for the particular device. And the key, I think, takeaway here is that from a developer's point of view and a user's point of view, the kind of the flow of how the APK works is the same, and hopefully you're just going to get faster, a better experience. This is a little bit of a picture of what it looks like when you're running the Dex2Ode tool inside, if you were inside the tool. We actually start up a minimal runtime that loads the framework code and some of the commonly used framework objects so that when we compile the code, we kind of have an idea of what the Android system you're running on looks like, so we can make optimizations specific for that target device. So once we kind of initialize this framework environment, we then go ahead and load the compiler and load the code to compile the application and generate an ELF file. So what does this ELF file look like? Oh, sorry, yeah, this is the ELF, kind of an overview of what these files look like. ELF is a standard file format for representing executable code. It is a standard file. We have kind of the sections you might expect. We have a symbol table, we have read-only data, we have some text that contains the actual code. One difference between how we use ELF files and more of a C, C++ kind of language would use them is we don't use symbols to find every single entry point, because typically a Java program has many methods, and having a symbol for each one that's unique would be too big. So instead we use the things that are already in the DEX bytecode, type indexes and method IDs to identify things, and we have this OAT data structure that we instead look up using the symbols in the symbol table. And once we have that OAT data structure loaded, we can quickly navigate when we're loading a class to find all the methods for a particular thing and link them up so we can execute the code quickly. One other thing that we do that's a little bit different is we actually keep the original DEX files around in the metadata in the ELF file. We use that for sort of the class metadata for loading classes. We also use it for other purposes, such as when you want to run the debugger and single step through your code, we keep the original code around so we can give you an accurate debugging experience. Oh, one final thing to note here is that in the compiled code for the class on the box at the bottom, you can see it actually does have direct links into the framework code as well as framework objects, so we can efficiently call things and not have to do runtime lookups to find references to frameworks code, which generally speeds application execution. So this is just kind of a time-based view of what compilation looks like. On the lower left, we have a sys trace of a compilation of a pretty meaty app. It's running on a 4-core device. And I've tried to break out the colored boxes on the lower left there to the right so you can kind of get an idea of what's going on there. And I'll talk through that. You can see most of it actually does get good parallelism during compilation. That's part of like taking more advantage of the modern devices, whereas the DexOpt and other tools for Dalvik were more single-threaded. So we do have a serial phase at the beginning where we extract out the DEX files for processing, but then we do a pass, most of the passes are parallel. And the first pass is class resolution, where we basically load all the classes, load their fields and methods, and this is where the compiler learns what the layout of a class is, what the label of the vtable is for the methods in the class, so we can, again, use that later on during compilation. The next phase is class verification, where we walk through the bytecodes of the class. For almost all methods we encounter, we find that they are verified, and we can mark that class as verified, and again, skip doing that during every runtime. One other thing we do, there are cases where we have failures during verification. So for example, if you install an APK that's maybe meant for the L release and you install it on KitKat, you may reference new APIs from the L release. And so we deal with that by inserting, we're noticing this is noting it as a soft failure during verification. We mark that one thing, and so later on when the compiler compiles, it can know that, well, I'm not sure if this code is available or not, and put a slower path in so that we can do the correct thing and handle it if the code accidentally goes down this path of calling a method that doesn't actually exist on this release. So if all that passes, we do this pass called the initialization pass, and we actually check for any any class that was properly verified. If it all verified okay, then and it has no class initializer, we'll go ahead and mark it as initialized ahead of time so that we know when we're compiling code that references that class that we don't have to do any class initialization checks. Again, another optimization for object-oriented programming. And so finally, you can see we've spent not quite half the time, but a lot of time with the program down there through that purple section doing verification, and now we finally start to do compiling. And this is where the compiler driver takes over and directs the different methods to different compilers potentially, choosing to compile for native code or JNI bridges or just doing dex to dex for things that we're not commonly run as class initializers. We don't waste time or space compiling them. So finally, we have a link step where we combine all the references between the compiled code and any references to the frameworks code and metadata, and then we link that together and we write out an ELF file. So what does this get us? So this is the slide from yesterday's keynote. I wanted to go into a little bit more detail. You can see here the blue bars are the Dalvik JIT as a baseline. These are on Nexus 5, kind of an AOSP build from recently around L snapshot time. The red bars show the ARC performance, and as you can see in our kind of collection of common benchmarks, we are doing better than the Dalvik JIT. The lowest number there is the Antutu composite score, and I wanted to just talk about that for a second because it's a composite of some things that are running DEX code and some things that are running native code, so we can only get improvement on the parts of that composite benchmark that are running DEX code, and we do get some improvement on those areas. A lot of the other benchmarks, you can see we have those general kind of bars of improvement. Many of those are kind of these historical benchmarks like Drystone that are Ford Porter from C or Fortran or something, and they're not really written in a Java style. What we really like is the chess bench score, because that's actually more reflective of like an Android developer writing object-oriented code in a modern way. What are the benefits they'll see? And I think hopefully that's more representative of what you'll see for most applications doing kind of compute in Android. So with that, just a reminder, this is kind of a snapshot of where we are now. We have additional work we've been doing in AOSP that hopefully some of that will make it into L, so we'll have more performance boosting things before we ship. And with that, I want to introduce Ian Rogers, who's going to talk about other performance boosting things, the ARC garbage collectors.
So, thank you, Brian. So, very loud. So I'm going to talk about garbage collection and basically how we're going to achieve fast allocation. What we've been really focusing on, less jank, giving you a buttery experience when you're using Android, and minimizing the memory footprint. So what is the memory manager trying to do? We're trying to allocate objects inside our application. We need to track on behalf of the application whether those objects are still in use, whether they're live, and we need to reclaim them when they're no longer in use. We want to do all of this, and we want to do it for free. And this is a real advantage in the Android ecosystem, is that this burden is taken away from the developer. So let's think about memory management schemes. There's no approach which is free. If you have native code, you have to worry about when you're allocating objects, when you're going to reclaim them. You have to worry about complex data structures, which might have cycles in them. You have to worry about multi-threaded issues, like when an object is accessed by multiple threads. So there are costs associated with that. If you're using reference counting, then you can find that a thread that lowers a reference count suddenly ends up having to reclaim all of the garbage in the known universe. And all of these things can create a lot of work on an application thread and cause significant jank and problems for the application developer. So what we've been focusing on in Art is making GC something that doesn't get in the way of the application and doesn't get in the way of the application developer, so they're freed from worrying about it. And our principal consideration has been how to reduce jank. And this comes around from pause times from the garbage collector. And I'll go into detail about that. So let's look at what's going on inside a garbage collection. Here we have some threads, the wiggly lines. We have a heap, which is the rectangle, and inside the heap are green and red rectangles, indicative of live objects, which are in use by the application, and dead objects, which are objects that the application can no longer access. The blue object on the left is an object that we're trying to allocate. So the job that the garbage collector's got to do is at allocation time, it's got to find places for objects to fit in, to get allocated. And it's also, at GC time, it's got to go and find all of these live objects, these green objects. And having found all of them, it then has to go and free them up. So let's see what happens inside of Dalvik. When we're going and finding this initial set of live objects, Dalvik will suspend the application threads. It also suspends threads inside of the virtual machine. So we tend to refer to these threads as a whole as mutator threads. They mutate the state of the Java heap. And to do this, Dalvik suspends these threads so that it can crawl their stacks and find what objects those stacks are referencing. Once it's determined this initial reachable set, it then traverses it in a concurrent phase. So the garbage collector is running alongside the application. Once it's found all of the objects, it then goes and does another pause. The reason for this pause is to make sure that the application wasn't playing any games with the garbage collector and hiding objects which the garbage collector thought it had already processed. In this phase, the card table will be examined by the garbage collector. Finally, having determined that everything has been marked, the garbage collector restarts all of the threads, and it concurrently sweeps and frees up the objects which were allocated. So in Dalvik, the pauses have been highly optimized, and the first pause is around 3 to 4 milliseconds, and the second pause is around 5 to 6 milliseconds. But the sum total of that is about 10 milliseconds. If we're going to achieve 60 frames per second, we need to be able to render frames in 16 milliseconds, and taking 10 milliseconds for garbage collection pauses out of that 60 milliseconds means we get dropped frames. So here is a systrace of Dalvik running the Google Play Store. And we're doing a fling, so we're scrolling down and allowing lots of bitmaps to scroll by, and the bitmaps are causing objects to get created and triggering GCs. And at the top, you can see what's running on each individual CPU. Beneath this are the vsync events, which are the screen refresh events. Below this, we have the vending application, the name of the Play Store application, and it's rendering frames, and you can see that in the dark green. And ideally what we would see is with every vsync event, there would be some dark green. But you can see in the center here that the dark green isn't there, and that's because of a dropped frame. It was caused a drop frame. At the bottom, we've got the view of what's going on inside of Dalvik. And we can see that there are GCs going on, there are explicit GCs going on back to back, and that there are pauses within this. And we can see that this second pause came in just before the vsync event where we had the dropped frame. So this isn't good. This isn't giving us the buttery experience we want on Android. One of the things that was on that systrace is we saw that the GC cycles were happening back to back. And why was this happening? Well, the application was trying to avoid a pathology and kind of like what happens in Dalvik's behavior, where Dalvik is trying to avoid heap fragmentation and allowing the heap to grow because it's worried about large objects getting reclaimed and then small objects coming in and fragmenting the heap, making it so that there aren't places where large objects can come and fit into the heap. So this is kind of shown on this graphic here. We've got the large blue object. We fail to find somewhere to fit it. We're worried about fragmentation, and so Dalvik is going to suspend all of the application threads and do a GC for alloc to then go and free up all of the objects it can to hopefully do a better job at fitting this large object into the heap. What does that look like for the application? It looks like one large pause. And these pauses are typically around 50 milliseconds, so this is going to translate into 4 dropped frames. Here we can see, again, a systrace of a Google Maps application this time. And we can see that we've got 2 GCs happening at the bottom. And in this situation, the 2 GCs have caused a pause of around 60 milliseconds and 4 to 5 dropped frames. So for art, everything is awesome. We've fixed all of the problems. Open bugs if we haven't, please. So we've made the garbage collector faster by new garbage collection algorithms. We've reduced the number of pauses and made the pauses themselves shorter. We've taken ergonomics decisions and strategies to reduce the amount of fragmentation so that we no longer need the GC for alloc. And we've done all of this with support for things like moving and compacting collectors and ways that allow us to use less memory. So what do pauses look like in the art's garbage collector? Going back to the earlier graphic, we've got rid of the first pause. What we do to create this initial set of objects that the garbage collector needs to traverse is the garbage collector requests that the applications go and mark their own stacks. So this is a very short thing for the application threads to do, and after they've done it, they can carry on running. So there's no need to suspend all of the application threads. So this checkpointing, as it gets called, gets done first, and the garbage collector waits for that, and then it enters the concurrent phase that we had before in the Dalvik CMS scheme, where we go and mark all of the objects. Then we have the second pause, and we've managed to make this pause a lot shorter than the Dalvik pause. We've done this by tricks like card pre-cleaning, where we take work out of the pause and do it ahead of it, and then we just double check that what we did before the pause was correct. If we look at a systrace, this is going back to the Google Play Store application and doing a fling. We've got the vsync events and frames being rendered. We've got a garbage collection pause happening just where the single pause is indicated, and no drop frames. The other thing that you can see on this systrace is that the GCs aren't occurring, the back-to-back GCs that was happening in the Play Store before, and that's because art doesn't suffer from the fragmentation problems that Dalvik had, and so we now treat the system GCs as something that are optional, and we only use them as a hint that we should trigger a garbage collection cycle. Whereas with Dalvik, they would always trigger a concurrent garbage collection cycle. And so there are no dropped frames here, and that single pause is measuring about 3 milliseconds. So that was kind of like a lot faster than the pauses that you're seeing in Dalvik. So how did we get rid of the GC for alloc events? So the problem we were having in Dalvik was these large objects were coming in, and these large objects would be bitmaps in the common case. And so what we do in art is we move the bitmaps out of the main heap and put them into their own separate, still part of the managed heap, but it's a separate area in the managed heap, especially dedicated to large arrays of primitive objects. And this is also useful for us because we know that by definition, arrays of primitive objects don't have references to other objects. And so we can improve the bookkeeping and the performance of the garbage collector as a consequence. What does this look like for an application like for Google Maps? So on the left, we've got the concurrent mark sweep GCs happening in Dalvik. The first pause around 3 to 4 milliseconds, the second pause around 5 to 6 milliseconds, and total coming in at just under 10 milliseconds. These are times from a Nexus 4. The GC for allocs was typically taking, the average one was around 54 milliseconds, and so that translates into a lot of dropped frames. What is art looking like in the same test scenario? Well, the average pauses are coming in at 2.5 milliseconds. So that's around 4 times faster. We've also found that one of the areas that we needed to improve was in terms of our allocation performance. So we were working with the Google Spreadsheets team internally inside of Google, and they were really excited by art because they'd been experiencing some bad performance. And so they switched over to using art, but they didn't realize the full performance of, that they were expecting to see. So you can see that on this bar chart. On the left, normalized to 1, is the Dalvik performance. And when they switched over to using art, they managed to get a 25% performance improvement on a Nexus 4. However, they wanted more. They wanted the 2x. They wanted the 4x. So there are other things we did in art, having seen this. So one of the things was we started specializing the allocation paths so that the allocation paths can allocate certain classes of objects faster than others by knowing things like the size of the object ahead of time. And this achieved a performance win, but not the dramatic performance win we would really have liked. So the next thing that we did was something that we'd wanted to do for a long time, and we implemented our own memory allocator. So Dalvik and art in KitKat, we're basing it on top of Doug Lee's memory allocator, which is the common one used in Unixes and so on. And this supports malloc and free, but it's not really tuned for Java, and it's not really tuned for a multi-threaded environment. So to make sure that it behaves in a correct manner, it has a single global lock around it. And so the garbage collector could be freeing things, and that would conflict with the application trying to allocate objects. And if you had multiple allocations happening at the same time, then they would get run sequentially. The rosalloc, as we call it, the rows of slots allocator, has a number of optimizations to improve performance. The first of which is that small objects, these small temporary objects that is so useful in languages like Java, they get allocated in a thread local region. And so because the region is thread local, this means that allocations can occur with no locking and no kind of sequential behavior. For larger objects, the bins that they fit into have their own individual locks. So that, again, it's reducing the contention for the locks, and there's a lot more parallelism. This is translated into a huge performance win for this benchmark, and you can see that the memory allocation performance has improved 10x. So we've been working on a number of different garbage collection algorithms for art. We're making art into a framework that developers and partners can come along and contribute to and improve upon. The first new garbage collector that art added was a sticky garbage collector. The sticky garbage collector takes advantage of the fact that we can know what objects were allocated since the last GC cycle, and because the generational hypothesis tells us that these objects are the most likely to be useful to be freed up, then we focus our energy on these. And because garbage collection time is proportional to the amount of live data we're going to process, and we're going to process less because we're only going to consider the live data since the last GC, the sticky GC is typically running 2 or 3x faster than the current garbage collector and reclaiming the same amount of memory. When the sticky garbage collector can't run, we run the regular CMS collector for either the applications heap or the applications heap and the zygote. And the ratio between running the sticky garbage collector and the regular concurrent garbage collector, we tend to run the sticky one 5 times for every 1 time we need to run the partial one. We're also working on moving garbage collectors, where this slide comes in. And what are moving garbage collectors? So moving garbage collectors, they want to do the same root set creation and marking of objects. But what they want to do during the sweeping phase is they want to move all of those objects together. And this basically removes all of the fragmentation and so on. We do this in Art via 2 approaches. We have a semi-space garbage collector, where we create a new memory region, and we evacuate the objects out of a heap and into that newly created space. And we also have a mark compact algorithm that's coming online at the moment, where we compact things in place. So moving collectors are good. There's less fragmentation. It saves heap. The downside to them is that if you're going to be moving objects around, the effect of moving an object has to be seen by the application atomically. There are 2 approaches you can take to doing this. You can introduce read barriers so that the read barrier handles the fact that the object is moving around in the heap. Or the most common approach is just to suspend all of the application threads again. And this isn't good from a GC-jank point of view. So we want to use the moving collector to compact the heap and get these memory savings. So when can we do it? So we know certain things about how applications run in Android. We know that it's worthwhile to compact the heap during the zygote startup, because if we save space in the zygote, we're going to save it for every application after the Android runtime is up. The other place we can use compaction is when applications go into the background, so when you press the home screen. And so we have various ergonomics determining when it's a good idea to run, to switch the garbage collector over to a compacting algorithm. We have various means of determining whether an application can perceive jank. We don't want to do things like have the play music application, which isn't a foregrounded application. We don't want to have jank in that because that would give you choppy audio. So hopefully we've done our jobs right and it's all working and so on. And so you'll get less memory usage. So with that, let me hand back to Anwar.
All right. Thanks, Ian. So a few words about 64-bit support coming with L. So it's one of the major new features of L. Our partners have been shipping or ready to ship 64-bit SoCs, and we're working pretty closely with them to make 64-bit user space happen. So why 64-bit? Well, you might argue that we don't need the additional address space now, but if you look at the keynote yesterday, Android usage is diversifying pretty rapidly from wearables to TVs, and bearing this in mind, I think it's really and there's definitely value today in supporting 64-bit. We see nice performance gains in 64-bit apps running on 64-bit capable cores. There are new instructions, domain-specific instructions for media and crypto, where we get huge speed-ups that can benefit the entire platform. But even in general-purpose apps, we're seeing nice speed-ups. So we'll take a look at that first, and then I'll get into a few details of how we make this work. So as I said, we spec compute-intensive stuff to take biggest advantage of this. We're working closely with ARM, with Intel, MIPS, Qualcomm, and others to make sure that we really deliver on this. So what I'm showing you here is graphs of speed up of 64-bit apps over 32-bit apps on the same silicon. On the upper left-hand side, as you face the screen, I'm showing you speed up in terms of a multiplier. This is on Intel's Bay Trail processor. It's a 4-core SoC for some custom RenderScript scripts, and we're seeing some really nice speedups going to 64-bit up to and over 4x. For crypto, we use OpenSSL as a primary crypto engine. If you look at ARM64 support, ARM v8 support, on Cortex-A53 and Cortex-A57 for the OpenSSL speed benchmark. We're seeing some really nice speedups there as well. Again, this is used throughout the entire platform. Any application that's using Android crypto is probably going to benefit from this. And again, those are multipliers on the vertical axis, so we're seeing about a 15x improvement there. And even for native stuff, we're seeing some nice improvements. Panorama benchmark is a benchmark that we use internally to evaluate toolchain updates. It's meant to be representative of a user taking a bunch of photos and then waiting for them to get stitched together in a nice little panorama. What we see here is that on ARM's Cortex-A53 and A57 cores, simply recompiling it for 64-bit, we see up to 20% boost for this. And what that means to the end user is I'm sitting there waiting for my panorama. It happens 20% faster, but it also uses 20% less power probably in terms of CPU core. And that's a really nice thing. But what about art? So for art, we weren't really looking for big performance gains with 64-bit. Obviously, we were hoping. But we've been pleased with what we've seen thus far. We expected most of this to come again in the compute-intensive workloads. So looking at art performance here, this is on Bay Trail. We have on the left speedups of going to art 32-bit from Dalvik 32-bit. So they're getting some really nice speedups on SpecJVM, up to over 6x. But the cherry on top is that we get up to another 30% speedup going to 64-bit. And again, all these numbers, right, it's early days. There's a lot more tuning that we're going to be doing for 64-bit with ARM, Intel, and MIPS. So expect more to come from this. OK, so how are we getting this done? Well, as Brian mentioned, we have compilers for 64-bit, for x86 64, for ARM 64, and MIPS 64 coming soon. We've extended the Zygote model for app creation by having dual zygotes. So we have a zygote for 32-bit apps and a zygote for 64-bit apps. What happens when you launch an app or a service, we detect what ABI it needs or what ABIs it can use, and then we delegate to that zygote to start up the app. So what that means is that, and I'll say more about this later, is that your apps, your 32-bit apps are still going to work, right, in your 64-bit device. The other thing we were concerned about is memory bloat. How much more memory is this going to take, having two zygotes and then having 64-bit references? Well, in art, we're using compressed references. So we're using just 32 bits for object references on the heap. So that mitigates some of this concern. So the cool thing about this is that if you have an application that's just running on art, that's just DEX code written in Java or whatever, it'll just work, right? As long as there's no native code, you can just download that app, and if you have a 64-bit device, it'll run on the 64-bit VM. That's 85% of apps in Play Store that are immediately 64-bit ready, right? Developers don't need to recompile. They don't need to upload a new version or whatever. It just works, and it's ready for you for free when you get your new device. So another performance boosting thing that Art and L and our SoC partners are bringing you. The other thing is that we'll be shipping NDK support and RenderScript support for 64-bit with L as well. So you can take advantage of all that other compute-intensive stuff as well. OK, so to learn more about Art, there's a couple of articles you should check out on Android.com. The first one, Introducing Art, covers some of the same ground that we've covered here. The second one, Verifying App Behavior on Art, goes into more detail on how Art can help you find bugs in your application, especially around JNI. You should definitely check that out. And with that, we'll take questions. Thank you.
Can I start off?
Yeah, go for it.
Cool. So I was wondering how Art is going to jive with bytecode injection that might happen right after compilation or even at runtime.
Go ahead.
No, I'll let you do it.
Huh?
So maybe I'll.
Yeah.
OK. So the model that Dalvik has and Art continues is that for class loaders, we have to have everything that the class loader has backed up by a file. So Dalvik never had support for kind of like doing in-memory injection of instructions and so on. If you have a file on the disk, then this is something we can do ahead of time compilation for and put into our cache so that we're not regenerating it all of the time. So basically, it works the same way as with Dalvik. There might be a little bit more time when we're doing the compilation, so that you might notice something at the initial at startup, a pause at startup because of the compilation. But our compilation times are really good and really fast, so hopefully imperceptible.
Cool, thanks.
Go ahead.
What's the effect on the boot time compared to Dalvik?
So first boot, when we're compiling things can slow down a bit. Compile time takes a bit longer. And the scale of things we're really talking about is an app goes from taking 1 second to DexOpt to, say, 2.5, 3 seconds to DexOpt, right? But if you're doing that over many apps, it adds up. That's just at first boot, right, or after an OTA, which are relatively infrequent events. In general, we think boot time will be faster. The one mitigating thing, though, is that because we're doing compaction of boot time to really make the heap more efficient, there is potential to extend things, although recently I think a patch went up to optimize that down, so we'll only do the compaction sort of toward the end, so we're not extending boot time. But code should be faster, starting up system services and so on should be faster, and things should just be faster.
Thanks.
Weak soft references. I remember like the early days, soft reference had some sort of like issue in the Dalvik world, if that was ever true. Like all that kind of stuff, it still applies for the VM, the moving garbage collector.
So for weak references, the behavior is the same as Dalvik. So when objects are no longer reachable, the weak reference will get cleared. For soft references, we have the same strategy for clearing soft references. So with soft references, they only get cleared when you run out of heap. And so what we do is we determine the objects to free up using a fairly naive algorithm, which means that soft references are of questionable use. And it's considered good practice in Android to be using things like least recently used caches so that you can manage the memory better.
One more last time. Sorry. So say I have a cache with thousands of objects in memory. Is there any like advice to get the most of this new garbage collector performance? Like other than don't keep that many objects in memory.
No, I mean, I think we recommend there's the LRU cache in the framework that I think we recommend. I think the only thing there is responding to the usual framework lifecycle events to know when you should be trimming back the cache and things like that. I don't think there's anything different with our garbage collectors you want to do from a caching point of view.
Can you briefly elaborate on the dual zygote thing? So is that two separate processes and then it just determines which one to launch, or?
Yeah, it's two separate processes. Then we determine, so we've actually compiled, so one of the things that Brian alluded to, we do ahead of time compile of the boot class path, so the frameworks and core libraries. We do that twice now, once for 64-bit, once for 32-bit. Zygote starts up. We start up with the respective flavor of the image that we want to use in code, and then and then we delegate to whichever one launches.
Yeah, I mean, I think the main thing for people that aren't familiar with the Zygote is basically we pre-initialize this 32-bit, now a 64-bit app execution environment. We haven't loaded any code. And then when we're starting an application, instead of booting it from scratch, so to speak, we basically just fork a copy of that Zygote and then it starts up whatever application you're running. So yeah, we do have 2 zygotes now for the two 32-bit versus 64-bit environments. But from an application point of view, it's really just about having faster startup.
We mitigate some of the cost of that, by the way, by pre-initializing things into an image and having it stored on disk. That's all like pageable if it's clean. So it helps with the dual zygote situation in terms of memory pressure. We're out of time, actually, and they need to set up this next talk. We'll be right here to take your questions until just before the next talk starts. Please feel free to stop by the Android booth. We'll be hanging around there.
Yeah, we'll have some demos.
We have some cool demos you could check out and ask us more questions. So thank you.
Thank you.